when we're working with a camera, there are a number of abbreviations that we use. As we've done, we've seen that if I want to have a multi-lens system with one or two, or honestly, however many lenses we want, because a number of, most cameras will have a number of lenses. Well, those are going to be pretty much fixed into one place. So and the separations are going to be tiny. So what I can do is I can speak in terms of a focal length for the camera. Now, this means we don't have to worry about the individual lenses because whoever built the darn camera took the time to measure that for us. All right? An effect that this has is that when we're looking at, let's see, say, I should say this is the effective focal length. Suppose I'm looking at the magnification of an object. Well, the equation that we have for magnification is that is equal to the opposite of the image distance over the object distance. But take note that if I have a camera the effective focal length is going to be pretty small, on the order of millimeters to, at greatest, centimeters. Also notice that the image distance has to be contained inside the camera. If the image doesn't fit on the camera, then how are you going to have it hit either in an old camera, the film, or have it hit the CCD chip to be able to record it? The image distance has to stay inside the camera and therefore be tiny. Now the image distance is typically way higher. The object distance is typically far higher than the image distance because it has to be. If you're taking a picture of something, then in most cases, you're not going to be trying to take a picture of something very close to you. And in fact, most cameras, if you try that, they will have like a little thing saying, no, use this set of settings to take care of that. So that if I've got this case where the object distance is well higher than the image distance, then notice that the relationship is still, we define the effective focal length, f, so that this equation is still pretty good. But if the image distance is large, then 1 over the image distance is tiny. So 1 over a tiny number plus 1 over a comparatively not tiny number, or tiny number plus relatively not tiny number, is basically the relatively not tiny number. If I have, like if I've got a building that's 300 meters tall, and I put a turtle on top of that building, then nobody's going to say, oh, 300 meters and 4 centimeters, or whatever. They're just going to say, the heck would they call it 300 meters. So in this case, I'm going to say, okay, forget that, call 1 over the image distance, object distance plus 1 over the image distance is basically 1 over the image distance because the object distance is so big. That means that this equation becomes that 1 over the image distance is basically 1 over the focal length. So in this equation, I can write that the magnification of a camera is equal to negative, and again the negative sign tells me, is it upright? Is that positive? Is it inverted? is the final sign negative, the focal length over the object distance. And that's a much friendlier choice because the focal length is pretty much known and usually printed on the camera, and the object distance is much more easily measurable, and it's therefore convenient. Now, this used to be more prominent, this is certainly more prominent when we're working with actual film, but there is another characteristic of the camera referred to as the F number, which is the effective focal length over the diameter, and this is a measure of light gathering power. The larger the diameter, the smaller the F number. The smaller the F number, then, well, I mean, the larger the diameter, the more light is coming in over some given period of time. So, the smaller the F number, the more light is coming in. And so you can use that as a measurement of like, how long do I need to keep the lens open to get a certain amount of light to be able to, let's see, take a particular exposure.